Hey folks, in this video I'm going to look at two example problems that use the work equals a change in energy idea. This one doesn't involve kind of the nuts and bolts of the equation, and the next one does. So feel free to skip around. You can try this problem if you want, and then see how the answer turns out. Use it however you want. So we have this like fairly complex problem with lots of numbers in it, but basically we have a ball that's going to roll down a ramp. So, before we even get into the problem, we can draw it. The ball is going to roll down the ramp. So it's rolling, when it's at the top of the ramp, it's rolling at 3 meters per second. The hill is 4.5 meters tall. And when it gets down to the bottom of the ramp, it's moving at 7.4 meters per second. The mass of the ball is 0.1 kilograms. And so we have like a new type of question. So normally, in a conservation of energy situation, the ball has some speed at the top of a hill, and then it rolls down the hill and it's moving faster. But the question reveals something else. Because the question says how much heat was dissipated while the ball was on the ramp. And so this is a phrase that the AP exam tends to use to mean how much work is done by friction. Because when friction happens, there's a sliding of surfaces on one another, and that sliding of surfaces generates heat, and that actually takes energy away from the system. And so what we're going to do is we're going to set up an equation to work with this. Now, the equation that's in your equation sheet is delta E equals W, meaning the change in energy is equal to the work that's done. I don't write it like that because I'd rather kind of tell a story. The way I write it is initial mechanical energy plus work equals final mechanical energy. And it allows me to show the variables kind of in the sequence they would happen, where a system would have some amount of mechanical energy, and then maybe work was done on it or by it, and then there's some mechanical energy afterwards. And so the work has to come in between these two, and so that's why I write it like this. When I analyze the problem, I'm going to have to infer some things. So the first thing that I'm going to infer is that in this problem, it's an open system. Now, this one's kind of easy because it directly mentions dissipated heat, and that implies work, and so whenever there's work done, you have an open system. There's going to be some external force on the object. The other thing I'm going to infer is that I am going to, because there's a ramp here, that I'm going to consider the system as the ball-earth system. And what that does is it identifies the fact that the ball is part of the system, and therefore its kinetic energy is important. And then because the Earth is the system, the gravitational potential energy is important. So I'm going to consider specifically those two types of energy. There's nothing that stretches, so I'm not going to deal with that. And then I'm not including the ramp in this problem, and so the ramp is the thing that's going to aid in the dissipation of heat. And so that's an external part of our system, or that's external to the system. So that's going to kind of frame my problem. Now, this equation is basically just an idea. So I want to expand upon this. In terms of initial mechanical energy, based on what I know about the ball, it has kinetic energy. So I'm going to kind of, spread out here. Initial kinetic energy is something that exists. And the ball is at the top of this ramp. And so because it's going to move down the ramp, I will say that initially it has gravitational potential energy. What I'm doing there, I've done this in a couple other problems, but I'm basically saying that the lowest part of this picture is where there's no potential energy. And so the ball and the Earth store potential energy when they're here, and then not when they're there. And so that's it. So these two things together represent the initial mechanical energy. Then there's work, and I'm just going to leave it as a W for now because I don't know what I want to do with it yet. And then as far as final mechanical energy, well, the ball is at the bottom of the hill, so there's no more gravitational potential energy, but it is moving. And so the final kinetic energy is there. Now, if you wanted to be clever, you could start by rearranging this equation and just have it like ready to go. But I didn't do it that way. I kind of just like starting with this equation. But what I want you to notice now is it says how much heat was dissipated. Heat is a form of energy. And so specifically in this course, when we say dissipated by heat, we mean work done by friction. And so this is my unknown that I'm going to solve for. So what I'm going to do is I'm going to rearrange this equation so that it's solved for work. So when I fill in all of my equations, I can just like plug them into my calculator and be done with it. So if I rearrange this equation, what I arrive at is the work done to dissipate heat is equal to the final kinetic energy minus the initial kinetic energy minus the initial gravitational potential energy. And so I'm going to like calculate it and it's fine, but I want you to think about something else. The work done that dissipates heat, the heat is something that just like leaves. That's like why we say dissipates, that it just goes everywhere and it affects the particles around it. So this phrase means that the energy is going to leave the system. This value of work should be a negative value. And so the initial energy, mechanical energy, should actually be greater than the final mechanical energy. So that's just something that we should look for here. All right, so now looking at all the data, like I have the speed, the mass, the height of the ramp, the final speed, I'm going to expand every equation. So 1/2 mv squared minus 1/2 mv naught squared minus mg delta y. Okay, so a couple things about this, or really one thing about this equation. You can, if you want to, combine like terms. And you can just put an m in the front of the entire equation and then have a big parenthetical set of variables. You cannot cancel mass. The variable w doesn't have mass included in it. And so you can't divide mass away. You actually need the mass in this equation. So, do what you want, but I'm going to just plug in everything. This is going to be a big, long equation. I guess what I am going to do is I'm going to combine like terms, and I'm going to say 1/2 times 0.1 kilograms. And then, if I like combine these two like terms, the 1/2 m is common between them, and then in parentheses is going to be v squared minus v naught squared. So v squared is 7.4 meters per second squared, and then v naught is going to be 3.0 meters per second squared. So by combining these like terms, I save myself a little bit of writing, but this whole term is the change in kinetic energy. And then I'm also going to take away the amount of gravitational potential energy. So that little g, and then the height of the hill is 4.5 meters. So, this is like a big calculation to find the work done. But again, when all is said and done, like the answer should just pop up. So 0.5 times 0.1 times the quantity, 7.4 squared minus 3 squared, minus 0.1 times 9.81 times 4.5, and negative 2 point blah, blah, blah. And so the work done, and as far as sig fig goes, I'm really just confined to 1. So because the 0.1 kilogram just has 1 sig fig, the work done is negative 2 joules. So when you have a heat dissipated question, it's always going to be negative work, and it's work done by friction. Okay, next problem. Next problem gets into, as I kind of alluded to, the nuts and bolts of friction. So we have a car problem. And again, like if you want to try this on your own, you're welcome to. But I'm going to draw a very simple car. And that car is moving at 25 meters per second. It's slamming on its brakes at some moment. And then, so we'll talk about rolling a little bit. When tires are rolling, it's actually static friction that's acting. And it's the static friction that provides the force on the tires that propels the car. So when the person slams on their brakes, assuming they don't have anti-lock brakes, which most cars do these days, the tires are going to lock and the car is just going to skid. And so there's going to be, like a streak of rubber on the road, and at some distance later, the car is going to be at rest. And so this is the problem. So we're going to imagine a flat road because I didn't indicate anything else. And so, like, conceptually speaking, this car has kinetic energy, and then by slamming on the brakes, the road is essentially going to take the energy away. This is once again an open system because the force of friction is external to basically every system so far in this course. So, if something is sliding, it's losing speed, and that is energy being taken away by friction and turned into heat. The system is just going to be the car, and this is because we have a flat road. So we're not going to consider potential energy. We are only going to consider the kinetic energy of the car. So I'm going to try and tell this story the same way that I tried the last one. And so starts with some mechanical energy, work is done, and then it has some final mechanical energy. It's based on the picture. As I said, since we're only considering the car, we're considering the initial kinetic energy plus the work. And then what's weird about this is this car, because this was a flat road and the car's not moving anymore, the final energy is zero. There's no kinetic, there's no gravitational, there's no elastic potential energy. There's just no energy, no mechanical energy anyway. And so that's it. So great, maybe I don't even know what I'm solving for at this point in time. But I'll read the problem again. And it says, how far does the car skid before coming to rest? So I am solving for displacement, which is squirreled away in the work equation. So let me do a little bit of rearranging, and then we can work with friction a little bit. The work is the big variable that I'm solving for, and if I just swing kinetic energy over, it's equal to negative initial kinetic energy. Now I can expand, and I can say FD cosine theta equals negative 1/2 mv squared. Okay, so now we gotta talk a little bit. D is the thing that I'm solving for. So if you really want to, and I'm about to do it, you can solve this entire equation for D, and then be done with it when you put numbers in your calculator. So let's do that. I will divide both sides of this equation by f cosine theta. So the distance that the car travels is going to be equal to negative mv squared over 2f cosine theta. Now that doesn't look very pretty, but it is what it is. So this is 1/2, so it's mv squared over 2, and then divided by f cosine theta, and there we go. So here's the deal. We need to consider the force of friction, and so we need to analyze the free body diagram for this car while it's skidding. So the car has a weight. The car has a normal force. Those two vectors are equal to one another, even though I don't think I just drew them to scale. But that's going to be important. The car's on flat road, so those two vectors are equal, and that is helpful information. And then the force of friction is acting in the opposite direction as the car is moving. And so just, to kind of remind you of things we've talked about, the displacement of the car is forward, but the force of friction is backwards. That means that theta is 180 degrees. Okay. This means that the net force on the car is the force of friction. So I'm going to do some work like outside of this equation for a minute and just remind you that the force of friction, if we're talking kinetic friction, is equal to mu times the normal force. And we did this a lot in the forces unit. So this is the friction equation, and the normal force is a vertical force. Now, because the car is on flat road, I get to make the following assumption without really thinking about it too much, that the normal force and the force of gravity are equal to one another. And so this becomes very important. The force of friction, according to this free body diagram, is equal to mu times the weight of the car. That is this force right there. So my final step here is to substitute the force of friction into this equation and then solve for displacement. So negative mv squared over 2 mu mg cosine theta. That's a lot. I can cancel the masses, which is very interesting, and it means that basically the mass of your car shouldn't have an impact over how far the car is going to skid. And I imagine a lot of automotive companies would disagree with that. And so there's, an inkling that there's more going on than meets the eye to friction. So I now have this equation, d equals negative v squared over 2 mu g cosine theta. So let's plug all of our numbers in and see what happens. So I have negative. V was 25, so 25 meters per second, and that gets squared. Very important. It is not the square of negative 25. It is the negative of the square of 25. So the numerator should be negative in this situation. On the denominator, 2 times 0.95 times 9.81 times the cosine of 180. Now, you can do the cosine of 180 separately, and what's essentially going to happen is you do the cosine of 180, it's equal to negative 1, and so you can say cancel the cosine 180 and cancel the negative. In other words, you have negative on the top, cosine 180 makes it negative on the bottom, and so you are going to get a positive displacement, which is very good because the car is moving forward. So all I need to do is 25 squared divided by this little mess on the bottom, 2 times 0.95 times 9.81, and I get 33.5. So I didn't really do sig figs very well here, so we'll say 34 meters. So like, I don't know, 40 to 45 yards would be the stopping distance. That's a long way. This car was traveling at about 55 or 60 miles per hour. And so to take like almost half a football field to stop, that's a big distance. And so this is your introduction to work as a change in energy and also, car safety involving braking. Thanks a lot.